because everything should be working. Good, good.
So Jun, so it's a manual process of admitting people?
I think Niels is admitting people, or?
Well, I'm also all the time, but it's you look at everybody who wants to get in and you admit them apparently, right?
Yeah.
So there is a flag for setting up the meeting, which I didn't check, but you can do it such that everybody is just automatically admitted, which is way simpler. But I'll keep track of it as the presenters go along.
Yeah.
Yeah, Zhou just said we can turn off the waiting room so they will be admitted automatically.
Okay.
Yeah, that's probably a good idea.
That would be easier.
Yeah. Way easier. Let me do that.
Did you find it, Niels?
Yes, it should be. It is. It says on the homepage that no waiting room, so people should just come in.
Well, it does say 5 people are waiting.
Well, then you can apparently not do it after the meeting is started.
Yeah, it's increasing rapidly now.
Yeah.
So we just had to wait. Patience.
Since it's recorded anyway, I will start just on time.
Yes.
Yeah. Yes. I have a few seconds still to go, right?
Yep.
Yeah.
Okay, so I think it's time to get started here. Good morning, good afternoon, and good evening to everybody. It's so good to see colleagues from all over the world joining this initiative, the second top webinar. As probably many of you and most of you also joined the first webinar, so we thought this was a huge success and we found that it was worthwhile continuing with this. Unfortunately, last time we were actually overwhelmed with the number of participants, so we only had a limit of 300 people and some had to leave without even watching the webinar. But meanwhile, we have expanded this limit up to 500, and in principle, we should have a YouTube live streaming going on, but it has created some trouble. But definitely everything will be recorded and you can go back and watch your favorite talk also later on. We have 314 participants signed up. Right now we are at 140 people or more, I think continuously increasing. And so this is very good to see, and thank you again for coming. We already have planned for the next couple of webinars. So the third one will take place on July 21st and will be headed by Guangyong and Shiwei from Dalian. And then the fourth one will be in August 27th and headed by Jamie Guest from the US. And this is exactly something we are aiming at, to have this geographical diversity, So we both have webinar organizers from all over the world, and we also have speakers from all over the world. And we try in each webinar to distribute this also topic-wise. So today we have 5 exciting talks, again, from people from all over the world. Several of them are from civil engineering, but talk about general topics that I think are of interest to all of us. And well, we started actually, our keynote speaker is the guy who has the toughest time. It's almost, or it's past midnight in Sydney. And so Qing Li is very kind to stay up for all of us. And for that, he gets the honor of being the keynote speaker here. So I think I will actually stop the introduction here, just saying that Qing Li has 15 minutes. Then the next speakers will have 8 minutes for their talks, and we have 5 minutes for questions in between. We also have some time left after the last speaker. And if you want to pose questions, you can, of course, signal us, or you can write questions in the chat during or after the talk, and we will try to read them up or let you pose the questions. So thank you very much again for coming. And Qing Li, please share your screen, and the floor is yours.
Can you see the screen?
Yeah.
Yeah. All right. First of all, I would like to take this opportunity to appreciate the organizing invited us to share with everyone our work. I think this is a really important and good initiative to bring us together during this special time. Today, my presentation topic is the phase field-based level set topology optimization for maximizing the fracture resistance of brittle materials. So this is the agenda for my talk. First of all, I would like to give a little bit of background why we are interested to do this sort of study, and then talk about the phase field fracture model, and then level set based topology optimization, and finally give some demonstrative examples, and then give the conclusion. So the reason for us to look at this issue is that 3 years ago we had a significant issue. We did the sort of a tissue scaffold tissue engineering for sheep model, the animal model, and it cost us quite a tremendous funds to actually support this study over 12 months. And after we printed this ceramic type of sort of a scaffold places to the sheep long bone, and we used some sort of a fixation plates, and then we suppose actually everything looks quite strong, and we can obtain some good results. Unfortunately, it failed. So after we harvested the sort of scaffold, we found out the scaffold actually generated some cracks. So those cracks actually largely affected the sort of outcome of the tissue regeneration. So showing here, you can see the fracture induced some failure, stopped the sort of bone regeneration. Later, we look at the scaffold sort of a fracture. As you can see from the image here, really fractured in some place. So that was the first sort of example. We needed to redesign or optimize this sort of scaffold topology so that we can actually achieve proper results. And the second example we used for many people actually received the dental bridge treatment early days. So showing here, you can see some sort of crack pass through this sort of a bridge model. And the dentist asked us to say how to ensure this sort of a dental bridge structure is safe during the service period. For this reason, we tried to actually use topology optimization methods to optimize the structure. And in this particular case, we used the metal and the ceramic combined sort of a system. Later, we moved this to sort of all ceramic, but in different parts. So zirconia and porcelain sort of a, both are the ceramic materials, and try to maximize the fracture resistance. So this actually gave us motivation. Excuse me. What's the best actually topological configuration so that we can ensure the system is safe? And for this reason, we looked at the sort of a design problems. So showing here is a sort of a schematic. We have such a domain, and we try to actually place the sort of a reinforcement or inclusive materials in this domain so that we can maximize the fracture resistance. Take this opportunity, I would like to acknowledge some sort of a existing work done by two groups. One is led by Shah and another is in Colombia. So they used the phase field combined with ESO or phase field combined with simple model. So in this particular study, we want to actually combine the phase field with level sets. So let's look at the phase field model. So showing here is a different sort of modeling mechanism to capture the fracture or cracking propagation. Showing here is, as you can see, we can actually model the crack, and this is simply just using this continuity sort of a Baandrup interface. Alternatively, we can still capture this sort of a change of the media, but this time we're using smeared sort of a damaged crack. So in other words, we can use some sort of a phase field variable to model this sort of fracture inside of this media. So to do so, we can actually define the phase field variable D. If D is equal to 0, that means that there's no any damage. If D is equal to 1, it's completely damaged. In between, there's some damage, but may not completely fracture yet. So we can actually use this for model the sort of a system by using the phase field model to model the whole system. So the potential energy, this time we need to take into account the fracture energy and the strain energy. So these two components actually form the potential energy. Specifically, we can actually model the isotropic damage and anisotropic damage by using the sort of a phase field variable. So showing here is sort of a modeling details. And we can formulate the stress tensor and then bring this to the equilibrium equation. So this is a new system by using the phase field model. So someone, if you are interested to look at it, how to implement phase field, you can actually read this article. We implemented this in Abacus. So provided the code, you can download the code and do some case studies to actually model the fracture by using the phase field model. Now, after we have this phase field methods, we can further actually look at how to implement this phase field model, fracture model to the topology optimization. So showing here is our problem. We're going to look at this domain, and there is a phase field based sort of fracture. This is just a sort of a continuous model. And our question is that how to actually optimize these materials to how to optimize the inclusive reinforcement materials so that we can maximize the fracture resistance. So to do so, we use the level set formulation, and this is quite the standard. We just follow the standard approach to use the level set function to model these materials to sort of evaluation. So the objective function we set up for this optimization problem is that we try to actually maximize the fracture resistance. For this reason, we can actually use the mechanical work as an objective function. So mechanical work can be approximately actually expressed in terms of the sort of a whole or entire fracture or cracking propagation process. So during the whole fracture propagation process, what's the sort of a mechanical work? So we can actually add all these together to approximately obtain this mechanical work. And what we do is that in this particular, let me go back to this. So showing here, so we use the displacement controlled sort of loading. For this reason, we can actually, look at the displacement loads. So we apply displacement and try to actually apply displacement in a constant rate. So showing here is a formulation. And after that, we can actually further write the mechanical work in terms of step-by-step sort of incremental mechanical work. Now, we can actually we can define the objective or the topology optimization problem by using the mechanical work. So our purpose is maximize this or minimize the negative. And we can actually set up the volume constraints. And showing here is governing equation based upon the sort of phase field. And showing here is we actually use two different materials. Materials one used to be serve as a matrix. Materials two serve as a inclusion. The challenge is that how to actually derive the topological derivative. So what we do is that we try to look at the what's the sort of influence of creating a infinite sort of small hole in this domain in the sort of a shape functional. So this is typical sort of a formulation for sensitivity analysis. But the challenge is that the first, this is sort of a nonlinear problem. We need to take into account the progressive sort of a clock propagation. For this reason, we needed to actually linearize this sort of a nonlinear problem by using very small or short time steps. And then we can derive the sub-derivatives in a stepwise sort of fashion. And the total derivative can be just the sum of all these sort of a sub-derivatives. And we make use of the stacked sort of algorithm for each time step. And in this particular case, we ignored the topological change on the effect of topological change on the phase field because of the small time step. And this is more detail about the sort of Lagrangian cost function. After we introduce this sort of perturbation and then perturbation, we can see the difference. And after that, we can actually look at the topological derivative. So topological derivative can be approximately, can be just concisely expressed as this. And this follows in which you can see the U2. U2 actually is following the differential equation is given here. And that gives us really important sort of a clue. This is actually just come with the same shape as the previous sort of a governing equation. So for this reason, we solve this or solve the previous governing equation, we can obtain the self-adjoint sort of variable. So this is the step-by-step time dependence. And we can actually further write up the sort of a topological derivative in terms of the heterogeneous materials. In the showing here some sort of a more specific mathematics. I don't want to go through too much details. And this is a more detail. I want to jump to the time constraints. We want to jump to the examples. So this is a flow chart. One important thing is this is a path-dependent sort of a topological derivative. Let me go to the sort of examples. The first example we would like to look at sort of arrow shape. If without this sort of a reinforcement inclusion, and we can see the fracture, the crack actually propagate horizontally as shown over here. After we place this sort of a inclusion or reinforcement, we can see the fracture actually change the direction. So showing here is our topological sort of a design process. This is corresponding sort of a fracture process. And some people may argue if you want to block sort of a crack propagation horizontally, you can easily set up two bars, vertical two bars, and they can prevent this sort of a propagation horizontally, or just simply place such as square sort of a inclusion, or you can simply use the stiffness-based linear topology optimization. In comparison, if you look at the mechanical work, so we can see clearly this sort of proposed methods or just the phase field-based topology optimization provides the highest mechanical work to actually refract the structure. So this is a comparison. If you want to plot the mechanical force versus the displacement, we can see the proposed message actually generated the largest. Below this is the sort of energy, so it's generated the highest sort of mechanical work. So some people may argue if I place the design domain in different places, the results can be different, as you can see from here, but it comes with the same volume. So that basically this is our sort of design domain inside of this arrow shape. The second example I would like to show is that, so if we have this sort of a slab, come with two preset cracks, and how to optimize this sort of a inclusion topology. So left-hand side is sort of fracture resistant based topology optimization, and the right-hand side is a stiffness-based sort of design. This is more traditional, and showing here is our sort of a fracture process inside of the optimized sort of inclusion. And this is a comparison. If you really plot the force versus displacement, obviously this one comes with much higher sort of energy to fracture the structure. The final example I would like to share is that dental bridge design. So it's shown before, and showing here is this is our design domain. We really want to actually optimize the sort of placements of the sort of a reinforcement materials. Showing here is our optimized design. If you look at the fracture propagation process, that's just simply show through this sort of interface. All right, to conclude, first of all, we present the phase field-based sort of level set topology optimization for enhancing the fracture resistance. And in this particular study, we use the path-dependent sort of a topological derivative. So this is quite important. And finally, the proposed sort of a examples actually show the advantage of this type of study. If you know more detail about this study, you can refer to this particular paper we recently published. Thank you very much. Hope I control the time.
Thank you so much, Jing. We will give you the thumbs up here. So questions are open for Jing. And I think maybe we try with just speaking up to begin with, or make a mark that you want to ask questions. So
I have a question.
Yes.
Yeah, please.
Okay. Can you hear me, Professor Lee?
Yes, I can hear.
Okay. I think this is a very wonderful work, and the presentation is also very clear and insightful. So my question is that, to my knowledge, the fracture resistance, the measure of the fracture resistance is closely related to the boundary condition, right?
Yeah.
So my question is that in your research work, what kind of boundary condition? I mean, you prescribe the external load, or prescribe the prescribed displacement on the boundary, or both type of boundary condition are considered?
If we can, so in this particular study, we use the displacement controlled sort of loading. So we can of course use we can use the force sort of a loading directly. The displacement loading is relatively more stable to this sort of a modeling art. So for this reason, currently we just use the displacement control. So we can of course try later on the force, sort of directly apply the force on the boundary and see what's the difference, in particular for the topology optimization results. Okay.
So I mean, like, if you change the type of the prescribed boundary condition, maybe the sign of the objective function should be changed. For example, maybe from minimization to maximization, something like that.
Yeah, that can be, you're right.
So,
I agree.
So thank you very much. Thank you. Yeah.
So Qing, I have also a question. Qing, can you hear me? So this is
I can hear.
Yeah. So I heard that you are using the displacement loading conditions, right? So in that case, the adjoint equation should not be the same as the equilibrium equation when deriving the sensitivity. So in one of your slides, it is written that the adjoint variable is equal to the negative real displacement. So I have a question regarding this point. Yeah.
Is that right?
Yeah. Yeah. Here. Yeah. Yeah. Go ahead.
Yeah. So this is our governing equation, and that equation is similar to.
No. Yeah. You said you are using a displacement loading.
Yeah.
Yeah. Yeah. So here,
if you look,
the traction loading, right?
Yeah, if you look at this comparison with that one, so they have come with a similar sort of a formulation. So that means that we can actually use the sort of a self-adjoint solutions to obtain that.
Yeah. For this formulation, the adjoint equation is same as a state equation. That's right. Yeah. Thank you.
Yeah. Thank you.
I think Wei Chen has a question.
Yes, Qing, this is a very nice work. Can you hear me? Yeah, I think it's very practically useful. I have a question about modeling the fracture behavior, because fracture behavior is very much like a microstructure-induced behavior. So there's a lot of stochasticity in the process, and also it depends very much location dependent. So I wonder, how do you take in, I don't think this is something that needs to be done for this particular work right now, but I'm asking for long run, like how would you introduce stochasticity, and how do you introduce microstructure-induced behavior in this kind of process?
Excellent question, to be honest. Yeah, recently, our school recently got a sort of a 3D ceramic print. This is the first in Australia. So we try to print such sort of a 3D or 2D or 3D structures. As you can see, this actually printed the ceramics. The sort of a property actually changed dramatically from this group to another group. So really the stochastic or just the long deterministic design can be extremely important for ceramics or for such a sort of brittle materials. So we're currently working on this, try to actually look at how to, for instance, implement because the ceramics 3D print actually shrink dramatically. So how to take in the kind of shrinkage, how to take in the kind of the material, sort of a heterogeneity, and etc. So this is really actually we tried looking at in particular for the fracture. So also we need to take into account, this currently is a static fracture. We need to take into account the fatigue. Fatigue is another quite actually diverse sort of a problem. So I appreciate this question. Yeah, thank you.
Yeah, thank you.
Thank you very much, Qing Li. I think in interest of time, we will proceed, but at the very end, we will have time to pose extra questions to the speakers. So thank you very much, Qing.
Thank you, Ola.
Unshare your screen again. And the next speaker is Helen Fairclough, who will be talking about special truss parameterizations and optimizations, and I think also advertise some exciting software. So please, Helen. Oh, you should unmute.
Thank you very much. Yes, can you hear me now?
Yes.
Thank you very much, Ola. So yes, as Ola says, today I'm going to be focusing on truss structures. So these are particularly common in the sort of building type designs where we have really large structures. For example, this case study has a 50-meter span and occupies 3 floors of this building. And you can see on the top left a typical design that engineers might come up with for this problem. However, we took this problem and posed it to a truss optimization, and we found the result on the top right, which you can see has less than half of the material usage of the basic design. However, you can also see that this is far from being practical to build, and therefore today I'm going to be focusing on how we can obtain structures such as the one in the bottom here, where we have almost as much material savings as the fully optimized design, but much simpler to construct. So for those of you who are unfamiliar with truss optimization methods, I'll briefly outline them here. We have our design domain, and we discretize it by adding a set of nodes distributed throughout the space, and we then connect each pair of nodes with a potential member, and we can formulate our problem as a linear programming problem to minimize the volume subject to equilibrium and the limiting value of stress in each bar. And we find results such as this. We can also further refine them using geometry optimization, where we add the node positions as variables as well. So in the example I showed at the beginning, and also in this study where we've been looking at the design of long span bridges, we've been using a manual simplification method. That is to say that we solve the layout and geometry optimization and then take the results from that and use those as inspiration for these simplified designs such as you see at the bottom here. And we have found good results. We've found significant material savings. However, there's a lot of labor involved in this, and in some cases it may not be obvious how you should simplify a given problem. So today I'm going to outline two approaches by which we can simplify these structures automatically. Firstly, I'm going to look at the more rigorous but slower approach, and for this we're going to add complexity constraints from the beginning of the optimization process. So we take the layout optimization formulation that we had previously, and we add these new constraints shown here. We have a new integer variable for every node in the ground structure, and we have constraints such as allowing up to a certain number of them. So we've now got a mixed integer linear programming problem rather than just a simple linear programming problem. So it's more computationally difficult, but we do still keep the convex global optimum from it. So as an example, we have a simple cantilever here, and we've solved this allowing a maximum of 5 joints. And you can see that there are indeed 5 nodes on this structure that have bars connected to them. However, there's also this point circled in blue here, where we have 2 bars intersecting, which to the optimizer is not a joint, however, to an engineer clearly would be. If we want to prevent this, we now need to add integer variables for every potential member to say whether they exist or not. We then need to check every pair of potential members to see whether they intersect, and this is almost 12 million pairs that we have to check. And from this, we would find that almost 3 million of them would have to be an additional constraint to stop them from intersecting. So here we have those new constraints added to the formulation. And you can see this is now a very large integer programming problem, really far beyond what's tractable. However, we can still solve this if we use what is known as lazy constraints. And we use this to implement these bottom constraints here. So with a lazy constraint, we don't include it in the original formulation as we send it to the optimizer. Instead, every time a potential solution is found, we check to see whether any of them would be violated, and if so, we add only those constraints to the problem. So this is now much smaller, and we can try and solve it. So for this example again, if we find this solution as the potential bound, we do the check, we find that these 2 bars are intersecting. So we know that we need to add a new constraint to referencing those 2 bars, saying they can't both be present in any given structure. We reject it as a potential bound, and we continue using our branch and bound algorithm. We continue this until we find this final solution for this case. And to find this, we actually only needed to add 3 constraints to prevent 3 crossovers compared to the several million that we'd have had to add if we wanted to add them all at the beginning. So in this, we've reduced the computational time from a problem that wouldn't converge even given days of computing time to something that solves in about a minute. And again, we can refine it somewhat by using geometry optimization. So if we repeat this for different numbers of joints, then we can also do a nice parametric study where we get a Pareto front type graph showing the different forms. And this can be quite a powerful tool for designers to show where they want to balance between complexity and material efficiency. And again, each of the results shown there took a couple of minutes. If you're interested in more details about this paper, we have a paper that's just been published in SMO, and this also extends the method to looking at multiple load cases and looking at using the angle between members as the complexity limit. And we also show some problems, smaller problems where we can solve it without using laser constraints, and we can demonstrate that we have speed ups of at least 20 times. However, even though we have these significant speed ups, we're still looking at about a minute to solve these problems, which isn't quite quick enough if we want to make an interactive tool for designers. So I'm now going to outline our second approach, which is a faster but less rigorous approach, and it's based on a post-processing type approach. So for this one, we'd solve the layout and geometry optimization problems in the standard way. And our next step would be a modified version of the geometry optimization, where we're switching over so that we have the objective function is now to minimize the number of members, and an extra constraint is that we have a limit on the increase in volume. And instead of using integer variables, we're going to approximate those variables using a smooth heaviside function, so we can use a general continuous optimizing there. So here we have some results, and we can use different increases in volume to control how much complexity we want to keep in the structure. And again, we can simplify it using geometry optimization. And you can see here that this entire solution takes around a second. So this is much more useful for an interactive program. And we can also use it for larger problems. For example, here we have a 3D problem with 1,000 nodes and 2 load cases. And we have the benchmark solution, which took around 2 minutes to find. And then the simplification step took only 11 seconds. And you can see that there is only a very small volume increase and quite significantly simpler and more understandable. So this approach is the one that we've been using in most of our software that we have available. So we have a plugin for the Rhino and Grasshopper parametric modeling software that is quite commonly used in the building industry. And this lets you create quite complex 3D geometries, and you can interact with them parametrically. And we also have some webinars coming up focusing on this, starting on the 9th of July. More details about that are at the link given, buildup.org. And newly launching today, we have a new web app, and this has just been launched here and now. No need to download anything. You can simply open it in a web browser. It should work on more or less any device, and you can experiment and get more interested in truss optimization. Thank you.
Thank you very much, Helen. Maybe we just lost most of our viewers because they're going to play with this. But,
yes, ideally after everyone else's talk. I don't want to take everyone away.
But thank you for an interesting talk. So we are open for questions here.
Sorry, can you hear me fine?
Yes. Go ahead.
Sorry, it's Dirk speaking. Can you? It's not. Can you just go back to the slide where you illustrate the original problem you had? You had a slide with like a very messy truss structure. I just wanted.
That one?
No, earlier on.
Here.
Here, yeah. Yeah. Okay. I wonder. I wonder whether there might not be slightly more elegant ways to control. To solve the issue you're trying to solve, rather than adding all sorts of.
Sorry, somebody is making a lot of microphones if you are not speaking. Yeah, could you repeat the question?
No, it's not really a question. I just wanted to see the picture again. I just wonder. I maybe to put it to the floor. Whether there. Whether this is the sort of result we expect from a truss optimization. How much is that result just maybe a failure of the optimization algorithm, or in how the problem has been set up?
So the top right image there is very much a Mitchell type truss-like continuum, or a close approximation thereof. So we know that there are significant numbers of problems where that is the theoretical solution. Indeed, there are clearly many options for how we simplify things.
Okay, okay. Because I'm sort of thinking, because yeah, exactly. And you mentioned it at the end, you referred to heavy side functions and so on. And I think you can, by playing similar tricks that we play in continuum-based topology optimization, you know, driving materials to solid and void, and also filtering techniques and slope constraints and those sort of things to control geometric complexity. I wonder how much of that can maybe be used to solve your problem as well. But it's not. I'm sort of wondering about it. I don't have an answer. I don't have a specific question. But yeah, maybe someone else can comment on that. I don't know.
So Dirk might be thinking about penalizing if two bars are crossing without having a hinge. You would penalize them in some sense.
Yeah.
I guess, is that something you've considered?
Not specifically on the crossover, but in the Peregrine plugin, we have got, I believe, 3 different sort of things you can penalize using the heaviside function. We have number of members, and we also have constraints about the number of members meeting at given joints, etc., and the angles of those. So yeah, we have some of, but yes, you could use that approach for quite a lot of different specific constraints, even some of which might be specific to certain problems or things like that.
And then a quick question on connecting members, which is, I think, on the next, you had a couple of nice basic simple pictures. Here, also this, whether the members cross or not, you know, if it's again, if it's really an optimal solution and the members cross, but they should not be connected, then that's sort of what it should be, or no. You know what I mean?
Yeah, so we have in the paper also extended this to be so that you have a limited number of members, but that number of members includes sort of 1 extra for every time you have a cross. And yeah, we found that particularly useful in multiple load case problems where we use a plastic approach. So you get these sort of overlaid examples where you have almost 2 structures, one on top of the other. So we found that it was really helpful to be able to take that approach then.
Yeah, and to be concrete, to be specific, my feeling is just that this issue of complexity and the number of connections you have at a node can also be cast as linear constraints in some way. I just have a feeling, but I might be wrong. I think it might be possible, but yeah, maybe something to think about, or to maybe someone gets inspired at some point.
Yep, I'd certainly be interested to see it if anyone can find a way to do it.
Okay, thank you very much for discussions and presentation, Helen. So we will rush on to the next speaker, which is somewhat related because he will also speak about bridges and civil engineering structures. So Mads Baandrup, are you ready to share screen and go ahead?
Yes. I hope it's visible now.
Yes, perfect.
Okay.
Go ahead.
Thank you, Ole. So my name is Mads Baandrup. I recently defended my PhD from Technical University of Denmark with the title Innovative Design of Bridge Girders and Cable-Supported Bridges. And the work I'm going to present today is a recently published paper in Nature Communications with the title Closing the Gap Towards Super Long Suspension Bridges Using Computational Morphogenesis. And the work, both my PhD project and this paper, is about suspension bridges. And these are some of the largest man-made structures, and they facilitate very important infrastructure links and have often become landmarks. The part of the bridge that we have focused on is the bridge deck or the bridge girder, which is the part of the bridge that carries the traffic. And as you see, is suspended here from the hangars. The design principles of the bridge deck, they have remained more or less unchanged for the past 60 years. So we thought it was about time to see if we could reinvent this design concept and to make a more material efficient design concept. So further motivation for doing the work is that in suspension bridges, girder self-weight is critical, particularly in super long suspension bridges. And this is clear from this small figure, where you see a typical layout of a suspension bridge. We have the bridge girder carrying the traffic. So the self-weight of the girder and the traffic load has to be carried by hangers and main cables, which transfers the loads out to the anchor blocks, towers, and towers foundations. So this means that if we can reduce the material consumption and the weight of the bridge girder, then we can also reduce the material consumption in the remaining part of the bridge. Furthermore, more lightweight bridge girder will also allow even longer main spans to be constructed. Furthermore, the conventional design concept of these bridge girders, they are subject to substantial fatigue issues, which is a quite large challenge. So this motivates for identifying more efficient structures. And finally, the construction industry is accountable for 39% of the world's CO2 emissions, which really advocate for more efficient use of materials within the construction industry. So the starting point for our work was the Osman Gazi Bridge, opened to traffic in 2016 in Turkey. At that time, this was a state-of-the-art bridge design. So we thought this was a good starting point for our work. And as you see from the figure to the lower right, this is the conventional design concept. So we have outer skin plates stiffened by truss in the longitudinal direction and diaphragms spaced 4 to 5 meters apart, stiffening in the transverse direction and transferring loads out to the hangers. The model we use for the optimization consists of 3 sections of this continuous and periodic bridge girder. So this is a quite large domain. So to discretize this into small elements, we needed 2.1 billion elements to have an acceptable discretization. So we made an assumption about having a fixed solid top plate for the traffic to go on top. The outer geometry is similar to the conventional design, so we focused our work on distributing material within the interior of this domain. Furthermore, we fixed the 2 end surfaces. One end we applied fixed fixed boundary conditions, and at the other end we applied global section forces. And this is also part of the reason why we have 3 sections of this periodic bridge girder to impose boundary conditions and these global loads. Furthermore, we imposed a symmetry condition both along the longitudinal center axis and along the transverse axis of each section, which is similar to the conventional design because you have the same loading in both sides of the bridge girder. The loads we applied was both global load cases from a global beam model of the entire bridge and 2 local load cases to take account of more local effects. The optimization problem is the classic compliance minimization problem. So we wanted to maximize the stiffness in the center span for a given amount of material. And then we have the usual state equations as constraints, as well as the volume constraint and the box constraints on the design variables. The solver we used was the method of the moving isotopes. We used the density filter, and then we solved the optimization problem for 400 iterations over 85 hours on 16,000 CPUs. So the results we got from this optimization, you see here we have 3 sections of the bridge. First of all, we see that we actually have some transverse diaphragm looking panels. However, they are curved towards the hangers, so they transfer the loads more directly towards the hangers and then on into the rest of the bridge structure. We also see that these panels, they are spaced much more frequently, which means that we can have a thinner top plate, so we don't need this top plate stiffened by longitudinal truss. And if you take a closer look at the region around the hangers, we also see this longitudinal panel-like structure to support this high force region. However, this structure is quite complex, and it would be, in this scale, impossible to construct with conventional manufacturing methods. So we wanted to take a further step, which was to use this structure as inspiration for an interpretation of the design. So we came up with this design indicated with red panels, which is a design with a similar complexity to the conventional, but inspired by this gigascale topology optimization results. So compared to the conventional design you see here to the left, which is indicated by the blue panels, we have our interpretation with the red panels, with these curved panels towards the hangers. And by applying similar plate thicknesses as in the conventional design to our interpretation, we gained an improvement in stiffness or in weight of around 13%. Then subsequently, we did a parametric optimization to redistribute the material within our interpretation. And here we gained an improvement of up to around 28% or an equivalent weight saving of around 28%. So the conclusions from our study and in the paper are that we gained these possible weight savings in the range of 13 to 28%. And this is equivalent to a weight reduction or a CO2 reduction of the entire bridge in the range of 9 to 19%. And the layout we came up with by the inspiration from the topology optimized design was a layout with a slight increase in number of diaphragms. Some of the diaphragms were curved towards the hanger anchorage. And then we have this additional longitudinal support panel, which is not present in the conventional design. I think this work really demonstrates how topology optimization could and should be used in civil engineering. So we use the very complex results for inspiration and doing interpretation towards more simple designs. So this approach is really beneficial in the early design stage. So I hope you found this interesting, and the recently published paper is available open access. Thank you.
Thank you very much, Mads. We are ready for some discussions to this or comments.
Hi, Anne, Fred here.
Yeah.
So thanks, Mads. Very nice presentation. So in many civil engineering structures, not only the operational loads are critical, but also the loads during the whole building and assembly process. Have you also looked at that? And if so, how would that change the design?
Thank you for your question. We have not included loads from the construction process. So the load cases we have applied are identified from a global beam model of the entire bridge, with all loads from the final stage of the bridge. And it is correct that in the construction of suspension bridges, the load cases differ and can differ quite a lot compared to the construction stage. But I think for the deck itself, it's more or less governed by the loads in the final stage from wind and from self-weight and traffic loading.
Okay, clear. Yeah, thank you very much.
Yeah.
Hey, Mads, this is Jamie. Really awesome, cool work. Quick question for you on before you do the interpretation of the design. So you mentioned you did a linear density filter, and it looks like you have really fine features, right? So when you do the thresholding to form that sort of gray silver design in the top right there, did you end up changing the topology quite a bit when you changed that thresholding? Was there a lot of sort of gray regions, I guess, or did you get really clear structural members? Are those ones that you're showing actually a couple elements?
The filter radius was quite low, but I think we ended up with somewhat a clear structure in the after the threshold as well.
So the center members are really, they reach a unit density and they're meant to be there. Yeah. Okay.
Yeah.
Mm-hmm. Guangyong, you have to unmute.
Yeah, my question is, in civil engineering, people prefer the design with a very clear the force transmission path, because then it's easy to check. I mean, check if there's any fault. I mean, if the force transmission path is not so clear, very diverse, then it's more difficult to check the structure. Yeah, I finished.
Okay. Yeah. So it's a question of having a more or slightly more complex structure, and I guess these curved elements. I think we have highlighted the potentials and how things could be constructed more efficiently. And then I think for the checking and the actual design, I think that's another more practical discussion. But of course, that can complicate a little bit, but I think it should be manageable.
Yeah.
But Guangyong, I'm just curious, wouldn't you say that this is a clearer force transmission path? Because now the diaphragms go directly to where the hanger load is being transferred. So for me, it seems like an obvious and simpler construction than the one with the straight ribs.
Yeah.
But there are several civil engineers here, so maybe they will have to object.
I think the interpretation is important, right? The interpreted design is important and helps us get there. Yeah.
Okay, but I think we will continue here. Thank you very much again, Mads. And actually, we will continue to another civil engineer, and whether she can actually build these very complex structures, I don't know, but she's definitely looking into it, I think, using additive manufacturing processes. So next speaker is Josephine Carstensen. Please go ahead.
Thank you, Ole. I think I'll leave Matt to build bridges. I had 2 courses about it 15 years ago. So he's much more of an expert on that than I. I'm Josephine Carstensen. I'm an assistant professor at MIT. And I'm excited to tell you about our recent work on topology optimization with nozzle size restriction for material extrusion-type additive manufacturing. And there went half my time just saying the title of the talk. So additive manufacturing by material extrusion is really used in a range of additive manufacturing techniques, ranging in scale and material systems from bioprinting or bioextrusion over fused filament print fabrications or fused deposition modeling, to bigger scale construction techniques such as big area additive manufacturing and concrete 3D printing. And because of this wider range of possible applications, we are of course not the first ones to ever be interested in coupling topology optimization and material extrusion. And there's been done quite a bit of work for FDM and a little bit just touching on designing for concrete 3D printing. But none of these works have incorporated the fact that all of these processes usually have just a single nozzle that move throughout the design domain in a layer by layer fabrication method, and that the fact that this nozzle cannot change size as it goes along. So what you currently have to do is, if you get even a quite simple design, is that you have to take your design, prepare it in order to be ready for manufacture. And what we really want to do, as everyone else here, is move away from that and try to create designs that are ready for printing. We have done that in a density-based topology optimization framework, based ourselves on the idea of modifying discrete object projection. And discrete object projection is really an extension of the Heaviside projection method, where you have a design variable space where you do all your math, and then a physical finite element space where you solve your physics. And the way these two talk to each other in discrete object projection is that an active design variable creates 2 features in the physical space. And in the original formulation, these 2 features were a circle and a concentric feature, and it was used to include, for instance, stiff inclusions in a compliant phase material. We use this with the assumption that when a nozzle moves over the build plate and deposits material, it really does it by creating 2 regions, stiff, or not a stiff, but a core region where you cannot overlap nozzle passes, and then an overlapping thin region at the edges where you are allowed to create some sort of overlapping with an adjacent pass. And we're assuming that this is a material or a fabrication specific region size that the manufacturer would either provide you or you'd be able to somehow estimate. So this is something the designer sets. In this work that we've done now, we have assumed that these two regions have the same properties. So what we've done is that we have modified this discrete object that's projected so that it now has a circular feature, that's the center core region, and then it has these bonding regions exterior to it. And initially we said you can print going mainly in one direction. So the designer would choose, is my nozzle mainly moving horizontally, or is it mainly moving vertically across the build plate? You then project separately to get these pseudo densities, one for the core region, one for the bonding region, and then you combine it to get your final element density. Just to quickly run through how this equation is just constructed, if you have or are in an element that is either have one of the two features or pseudo spaces being active, then you will get a fully solid stiff element. If you are in an element where you're overlapping, so you have active features from both the bonding and the core region, you'd be penalized on the element density. And if you are in a void region, then nothing is really different from what we're used to. We're not doing anything very fancy with the problem formulation. We're solving for either output displacement or compliance. We've changed slightly the volume constraint to take into account that we have now these two material faces that describe the entirety of the material that's placed. And we're using this in conjunction with SIP to penalize the overlapping, and MMA is our gradient based optimizer. This here is our results for either horizontal nozzle movement or vertical nozzle movement. Horizontal movement looks like something that we're familiar with, especially along the exterior. It's much more difficult for the optimizer to be forced along a vertical movement. So we also see a hit in compliance for that particular result. Now, most printing processes are not forced to move only in a single direction. So we wanted to expand the movement of the nozzle, and we did that by introducing the placement space that we already had, and then also directional space. So now if we have a placement variables that says go, then it's creating a circular feature, and then depending on the magnitude within the directional space, it will rotate where the bonding region is. So if we have a low magnitude, we'll get a horizontal feature, and if we have a high magnitude, we'll get a vertical feature. And now the density is constructed in a similar way. I won't go through it, but by these three separate projections. This is our result for the more free nozzle movement. And here we get something that looks like what we're more comfortable with. And the nice thing is that when we look at maps of the design variables, we also get an idea of how should the print path be for the nozzle from the placement space. And then we have this a bit more difficult, perhaps, to interpret picture of how the nozzle is rotating throughout the build. I also have a couple of different examples where you can, of course, choose the size of your nozzle. You can choose how much is core, how much is bonding region, but in the interest of time that's running out of me, I'll be a bit quick and just show it as a teaser for you to pick up the paper. And instead, I will say that we've developed a technique that includes a nozzle size restriction and density-based topology optimization. Doesn't come for free, as nothing does in life. It increases the computational cost for the single directional designs. It's about 30%. For the two directional designs, where we've doubled the number of design variables, it's obviously quite significantly more. We're not there, it's not perfect. We're not ready to press print, and isotropy and the continuity constraint, which are also very important for these extrusion-type processes, is not currently considered. So we know what to spend the rest of our summer doing. I'm happy to answer any questions, both now and later. Thank you.
Thank you so much, Josephine. I'm very fascinating stuff here. So are there some questions? I think Martin Baugren.
Yes, very nice. I really appreciate that. It looked like you had the filter size and the size of the nozzle the same. So could you perhaps have a larger filter? I mean, so when you reduce the filter size, you get more elements in your beams.
Yeah.
Could be interesting maybe to have two types of filters there, so you can control the feature size separately from the size of the nozzle.
So I didn't show that. I think what, if I'm understanding your question correctly, you can do that. The user prescribes how much do I want to be bonding, how much do I want to be core region. This inverter example here is the same nozzle size, designed with the same nozzle size, with more core region or less core region. I think I'm pointing opposite, but that affects the results, but you can totally do that.
But you go back to the MBB beam or whatever it was.
Mm-hmm.
Yeah,
so this, yeah, here
so when you have a smaller nozzle size, you get also more members.
Yes, yeah. So here, these examples here have kept the ratio of core to bonding region constant, and then just varied the size of the nozzle. And obviously, as you say, you get finer features if you use a finer nozzle. And the trade-off in complexity and compliance, I think most of us are familiar with.
Yeah, okay, thanks.
Maybe I could ask a question. So yeah. I didn't fully get that you regularize the angles, or can they sort of change as they want in every pixel or every point?
So in the first bit, they can't. In the second bit, they can. They can only, right now it's only set to change between 2, but I think you could make an extension where you allow more free rotation.
So when you have a line going sort of diagonally, then it's constantly switching from horizontal to vertical to horizontal to vertical. Is that?
You can also so it can also make, because it's a circle, it can also make diagonal lines without overlapping up to a certain angle. But it's more difficult for it to switch completely.
Okay.
So you can make a build up that's kind of not perfect with just 2, but gets pretty close.
Yes, thank you. We have time for one more question if there's somebody. Jun?
Yes, very nice talk. I have a question about the collection between the beams. So in our experiments, when the beams become very small, and because the two paths is not continuous, the collection is very weak. And I'm wondering, do you have some thoughts on how to solve this kind of problem, the continuity of two paths?
Yeah, so that's an excellent question. I think that I haven't done it yet, so I don't know, but my feeling is that maybe if you change the material properties between the 2 regions, so that the bonding region has a lower stiffness, that will kind of encourage that you within the load paths get more continuity and less build up as we currently see. But I'll tell you more about that in like 6 months' time.
Okay, thank you very much, Josephine. You can then come back in the 15th top webinar maybe. So thanks again, and we will proceed to the very last speaker, who is Jianguang from University of Dalian. And we are shifting sort of topic now and going to large-scale eigenfrequency optimization. So please, Zhang, go ahead.
Okay. First of all, I would like to thank all the organizers for inviting me to the webinar. So today I'm going to talk about a method for successive iteration of analysis and design for large-scale eigenvalue topology optimization. So in short, SIAD method. So there are different forms of eigenvalue-related design problems, including the maximization of natural frequencies, forbidden frequency intervals, and frequency gaps, and also phononic and photonic metamaterial designs, and also linear buckling designs. So if the structure is very complex, you may have to use a large number of finite elements for accurate analysis. So here, this is a typical frequency maximization problem. As we all know, for large-scale topology optimization, a majority part of the computational cost is devoted to the finite element analysis. For a static problem, as an example, with 12 million doves, solving the state equations accounts for over 95% of the total computing time. So the situation is even worse when a higher order repeated eigenvalues are of interest in the design problem. So this motivated us to develop a more efficient method. So let's first take a look at the conventional approach, the nested double loop approach. An eigenvalue design problem is essentially a nested double loop minimization problem. The inner loop is eigenvalue analysis. One usually starts from a set of initial Choi eigenvectors and then obtain the exact eigenmodes using kind of iteration algorithm. So this process is very expensive, but it provides the search directions of the outer loop design optimization problem. So in our study, we first asked ourselves a question. Should we really need to find absolutely accurate eigenvalues and eigenmodes for an intermediate design, which is not so important in the whole design process? So the answer is no. In our method, we first use some crude estimation of the eigenvalues at the first stage of the optimization, and then we gradually improve their accuracy along with the design iterations. So the basic idea is to use only approximate eigenmodes to calculate the eigenvalues or the Rayleigh quotients and their derivatives. And these eigenmodes will be improved along with the design through a linear algebraic equation shown here. So for the most, for the simplest case of fundamental frequency, in each design iteration, we solve the linear equation here only once in order to improve the eigenvectors. This equation is very similar to the inverse iteration, except that here the mass matrix and the stiffness matrix are not constant anymore because the structure design has been evolved, has been changed. Then we can approximate the eigenvalue with Rayleigh quotients and also its derivatives. So this is a basic idea. In our paper, we have also provided a discussion on the convergence issue of this method. I'm not going to details, but I only show the result. We have proven that the convergence of the method can be ensured as long as the design change in each iteration is small enough. So for case of higher order frequencies, we developed a subspace iteration-like procedure. So given a set of approximate eigenvectors, we first solve a linear equation shown here for just once, and then solve a low-dimensional eigenvalue problem, and then we update the eigenmodes. For repeated eigenvalues, we have to solve another problem, a sub-problem of eigenvalue analysis in order to find the Gatos differentiable eigenmodes. Now some examples. The first example is to maximize the fundamental frequency of a beam with 2.4 million doves. So this, we can see here that the method achieves a very steady convergence. And for 100 iterations, we only need to solve 100 linear equations. However, for the conventional double loop method, you have to solve over 1,000 full-scale equations. So on a desktop workstation, the double loop method costs about nearly 70 hours, but our method costs only 10% of that computing time. And both methods finally converge to nearly the same optimized designs and object function values. So in this slide, we also tested the method starting from a totally different set of initial eigenvectors. After only 10 iterations, our method produced very similar approximate eigenpairs and intermediate designs, and finally end up with nearly identical designs. So this is an example of 3D structure with 6 million dots. You can see that the convergence is also satisfying here. And this example involves higher order frequencies. In the iteration history, we can see that there are 2 eigenvalues approaching each other and became repeated eigenvalues. However, since we use the differentiable eigenvectors, we could still find the correct design sensitivities here. And in our ongoing work, we have also developed a so-called multi-step relay strategy for SID. So here we use different levels of discretization of the model. We start from coarse mass and then project the intermediate solutions of the eigenvalues, the eigenvectors, and also the structure designs onto the final mass. So this also helps us to achieve better description quality of the structure boundaries. So in this example, we maximize the second natural frequency using a 4 relay level of meshes. In the first level, we only use about 4,000 elements. And finally, in the final stage, we use 6 million dots. This design provides a smoother boundaries in the optimized design. Here we also see that this release strategy is very efficient. Only the last 20 iterations are run on the finest mass, and the first 3 levels of discretization cost much less time than the fine mass computations, but they provide very stable design. Here's the conclusions. So our method implements concurrent convergence of eigenvalue analysis and the design optimization. And also it provides a affordable solution of eigenvalue optimization with millions of dots on a desktop computer. So that's all. Thank you very much.
Yes, Jun?
Yeah, maybe a short question. The resolution looks really nice on desktop.
Thank you.
What kind of computation framework are you using? Like using a PETI or using some other framework?
PETI. So we implement this on in a parallel computing environment.
Yeah, thank you.
Yeah.
I had a question also. So you're not solving the eigenvalue problem in each iteration, but how do you make sure that you actually solved it at the end so that you know you have an accurate eigenvalue estimate? So do you have some requirement that you cannot stop the optimization part before you have an accurate eigenvalue?
Okay. So in the final stage of the iteration, we can ensure that the eigenvectors we have achieved is accurate enough. So in the final stage, we can ensure that the realist quotient is very close to the real eigenvalue of the design. But in the intermediate design, we only use approximate eigenvectors and approximate realist quotient, and also approximate sensitivities to evolve the design. However, we can improve that if the structure design is able to converge, then the eigenvalue analysis can achieve convergence in our method. So the details, can be seen in our paper.
Okay, thank you. So Federico Ferrari, please, you have to unmute.
Yes, hello.
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 Thanks for the presentation. And I have a question about this last point. So I can understand that you can prove that for a given design, you are using the eigenvalue, and so in principle, you can refine it and make it converge. My question is about how can you be sure that your design is converging? Because what I can understand is that you're using some sort of inexact Newton step, something like that. So it is true that you don't need the precise gradients to converge, but you have to ensure that your gradients are good enough. So is there a check in your code to relate your residual of the eigenvector to the residual of your optimization? Because otherwise you might, get lost at some point.
This slide shows the solution. We start from totally different eigenvectors. So these eigenvectors are actually selected ones. So here you can see that in the first iteration, this cosine-shaped eigenvectors is very crude, and the calculated eigenvalue is far from the real one. But after about 10 iterations, the eigenvalue become very close. This implies that the method has convergence property, and we cannot ensure the structure design using this method will definitely converge. But in almost all our numerical experience, they do converge to a very reasonable design. And here also, I'm going to show another slide here. So in the multi-relay approach, we use a very coarse mesh, and after the iterations, the eigenvectors can be improved, and they gradually improve themselves along with the structure design. So here, I can only see that in most of the cases, the method is able to achieve convergence. And we have also checked the eigenvector errors. They do converge.
Okay, thanks.
Thank you very much. Especially thank you to the last speaker, Jianguang. I think now we can accept questions or remarks to all speakers here at the end. It could still be to Jianguang or to some of the others if you are burning with a question.
Yes, I'm sorry. I'm burning with a question on the last presentation. This I'm curious. You said the proof you have. How do you link that? How do you link the optimization problem to the physics or to the state equations? Do you use the stationary conditions of the optimization problem?
No. We use a perturbation kind of a perturbation approach, and then we prove that the perturbation of the eigenvectors is linearly dependent on the design perturbations. So using this condition, we find that if the structure design converges, then the eigenvector results converge also.
Okay, so it's a link with the sensitivities, yes. Yes.
May I follow up on the question, Ola?
Sure, Fred.
Have you tried the method also for cases where the optimization proceeds, that many eigenvalues start to cluster?
Yes. That's what I was talking about. Okay, so no problem. We have used a subproblem solution to find the Gatoic differentiable eigenvectors. That means we have divided all the clustered eigenvalues into separate ones. So this is can be done for repeated eigenvalues, also for cluster eigenvalues. So the computation is not so complex. It's quite standard for the dynamic topology optimization.
Okay, thank you very much.
Yeah, thank you.
Thank you. So maybe I had a question to Qing Li. So in your talk, and we often see it because it's convenient to have an active volume constraint, especially when we have more materials. Sometimes actually there's no need for the second material, but we use it to show that it can design for several materials. So in your case, is there a need for the volume constraint in your problem, or would it choose the second material if it's allowed to? Or freely?
Not necessary. So the volume of fraction actually just make us to be more comparable for such results. So we don't have to have a volume of fraction constraints for the solution, because in many cases, for instance, in dental sort of processes, some cases we just use a single ceramic materials to replicate the processes. But in other cases, if for appearance purpose, we may need to have two different materials. The outside a little bit more transparent and more beautiful, and the inside need to be strong. So not necessary. But for the tissue scaffold, we need to ensure the porosity is higher than 50%, for instance. Some cases we need to ensure 70% and not 30%. 30% for the scaffold and 70% for the porous, so that the bone can actually fill the gap.
Mm-hmm. Okay, thank you.
And thank you.
Hugo?
Oh, cannot hear you.
We have to.
Okay now?
Yes.
Yeah.
Okay.
Yes, we can hear you.
Okay, Professor Li, I have a question. So you use the phase field model to simulate the propagation of the crack, right?
Yeah.
Yes. So can your simulation model can consider the case that the crack is closed, the closure of the crack during the deformation process? Yeah.
Yeah, currently we use the phase field variable, which range from 0 to 1. And very close to 1 means that the materials in that particular area are getting very soft, very weak, so that we can actually simulate the sort of a contact between in the interface in certain ways, which is different from the X-Fan approach. X-Fan sort of formulation allows us to actually model the real sort of a interface, so that we can make use of the contact. But in that case, the sensitivity is the issue. So yeah, if very close to 1, then we can say this is real, almost real crack.
Thank you.
Thank you. Federico?
Yes.
Another question?
Yes, I have two considerations about the bridge design. I'm thinking about the applications of topology optimization in civil engineering, and I talked about two things. The first one is in civil application, there is, from my experience, a problem with the tolerances, much more than in mechanical devices. So when you design something, then you have to think that this stuff has to be built in a, not with like a high precision machinery or something like that. So this is for sure one thing that has to be considered. And then another thing is maybe civil applications are the field for reversal of the structural optimization procedure. Usually we see from all the books that there is the size optimization, the topology optimization, then you can do shape optimization and size optimization. Well, I think the design of the bridge that you have shown tells another thing. Like first, you might do something parametrically where you define the placement of the ribs, and then you look the sides, then the shape, and then the topology. right? Because pretty much what you did was like we do a topology optimization larger scale, and then we reduce to a simple design. What do you think about that?
Yeah, I can follow your argumentation. But I think what we wanted to use topology optimization for was to identify, you cannot say the most optimal structure, but a much more optimal structure than the conventional design, to see how it actually looked like a more optimal structure. And then from there, be inspired to come up with a more simplified design. So yeah, I can see there's two different ways to do optimization or two approaches. And of course, there's a challenge in civil engineering also, as you mentioned, with the tolerances, and so and you need some more simplified designs. So how you end up with the simpler designs is, I guess, there's different ways to do that.
Yeah. Thanks. And one last thing about that, the second consideration was that in civil application, from my point of view, there is another challenge, that is the simulation then, because sometimes when you have a bridge or skyscraper, something like that, you have to take a full-scale analysis. So if you complicate the design, then you have to come up with a method for doing a reliable full-scale analysis of something like that. So maybe some homogenized model has to be developed for those designs. Yeah.
Yeah.
Thanks.
I agree.
So Ola, can I have a question to Federico?
Yeah. Sure.
So okay. So in our experience, when doing eigenvalue-related topology optimization, I mean the natural frequency maximization, we find that the optimized structure doesn't favor a design with many thin structure members, with many details. So this is intuitively correct and understandable. But I would like to ask Federico, if you have encountered a optimized design with many thin structure members when maximizing its eigenfrequency?
Well, you showed a clamped beam, right, in your slides. Like for a clamped beam, if you reduce the volume fraction and you put a not so high non-structural mass, you will develop some thin members.
Okay.
Because when you do natural frequency optimization, of course, the non-structural masses have a huge influence. The more you have non-structural mass, the more your design is closer to a static design. So that's another thing. I mean, what my question before was about, I mean, I can understand that you can show the convergence of the physics to a design, but I doubt that in general you can show that one step of subspace iteration is enough to have correct sensitivities to drive your design, especially if you have a very, let's call it dynamic optimization, like low non-structural masses and everything.
I think
thank you for your comments.
Okay, I think it's some interesting discussions that you should continue offline also. But just commenting on Zhang's comment to Federico's to Zhang's or whatever, it's interesting if you then go to buckling, then you see the small details again. Then you get the small struts again, like a hierarchical structure. So there's some interesting effects when you get to large scale, both dynamic and buckling problems. But I think I have to stop the discussions now. The clock is 5:30 in Denmark. And I want to thank you all for joining this, and especially to the speakers. And I want to remind you that the third top-up webinar will be on July 21st, organized by the Dalian people. Jianguang is showing his finger, so.
Yeah. Our host for the next session is also here today. Maybe we ask him to welcome everyone to the next session.
Oh, okay. So dear all, the next webinar, just as said by Ola, will be held next month in 21st. We are honored to be invited as the hoster of the next webinar. So we highly welcome all of you to join the webinar and bring your brilliant ideas and share your recent progress in the webinar. So we are looking forward to seeing you all in the next webinar. So thank you very much. Okay. Thank you, Ola.
Oh, thank you. Zhang also wants to say something. Yes. Yeah.
You are also welcome to suggest some topic. I mean, we can invite people, and you are welcome to suggest a topic.
That's super. Yeah. So thanks again to everybody. Have a nice day. Sleep well, or wherever you are in your day here, and enjoy the summer. So thank you. Bye bye.
Thank you. Thank you.
Bye bye.
See you next time.
Bye.
Thank you.
Thank you. Bye bye.
Bye bye.
Bye bye. Bye bye.